just because it's one of those things that we have to kind of grind into you, I'm going to ask if you can just think back to the other day and figure something out for me. Could you use the right-hand rule to figure out the direction of a force on this charged particle? So again, a magnetic field can't start a particle into motion, can't stop a particle that's already moving, can't change its kinetic energy, and it can't do work on a free particle in space. However, can do work on a current-carrying wire. So I want you to imagine I have a current-carrying wire in space with a current passing in this direction. I place it in a region of space that has a magnetic field. Now, the difference between a free particle and a current-carrying wire is that the charges in the current-carrying wire are trapped inside the wire. So although they're going to experience a force, all of them that are moving through the wire are going to experience the same force, but being trapped inside the wire means that they apply a force to the wire, and the wire experiences that force. So unlike a free charge, which is going to have its path bent, the entire run of the wire will experience a uniform force due to the magnetic field. Now, it's not much different than a force on a charged particle. The force on a current carrying wire is I L cross B. Bless you. Current isn't a vector, so the vector length of the wire is used as the cross product. This is the vector length of the wire. Again, I need to remind you or say to you, current isn't a vector quantity. It does have a direction, but it's not a vector value. Now, a couple things that I need to make sure I emphasize when it comes to using this expression. The only part of the wire that actually experiences the force is the part of the wire that is exposed to the magnetic field. So in the case of the drawing I have here, the actual length of the wire would be just the length that is incorporated inside the magnetic field. Any other part that's outside the magnetic field doesn't experience a force. But that force is a uniform value all along the wire. Based on the cross product, can you take a minute and tell me the direction of the force on this wire? All right, point in the direction of the force in this wire. Well, it's pretty good. Got a few people pointing in the wrong direction, though. First vector is the length, so I point my pointer finger in the direction of the length. Then my middle finger is rotated to point in the direction of the magnetic field, so this way. Now, before I move away from this point, and as we're talking about this, current represents the flow of positively charged particles. But we've come to understand that that's not what's actually moving in the wire. So in our concept of a current carrying wire, positive charges are moving this way, which matches our idea of QV cross B. If you do the QV cross B with this positive particle, you'll see that the force is also in the same direction. The force on the wire is this way, the force on the particle would be this way. But that's not actually what's happening in the wire. In the wire, we actually have negative particles that are traveling in the opposite direction. Try your right-hand rule on that. See if it changes your answer. So, is it pretty clear to you that even up to this point, knowledge of our magnetic force on a current carrying wire, it doesn't help us distinguish with whether it's a positive charge or a negative charge that's flowing through the wire? One of the things I want to impress upon you about the history of our conversation about electronics is that it took hundreds of years for us to figure out what was actually moving in the wire. This is still not a way to figure it out. Although we're getting closer, this won't tell us whether it's a negative particle or a positive particle moving through the wire, because the force on that wire is still in the same direction. Does that make sense? You see that okay? All right. Now, a couple of little station keeping things here I think that are obvious. Again, the L represents how much of the wire is actually inside the region where there's a magnetic field. This force is perpendicular to the wire, but also if your wire is curved, it's still going to be normal to the wire. So if you have a curved wire passing through a magnetic field, you could get a more interesting shaped force. But ultimately, we're going to deal with just nice, simple, straightforward ideas like this, where we have a straight wire passing through a magnetic field. Now, there's not a lot to add to this when it comes to a wire experiencing a magnetic field. It's very much in line with the same conversation we had for a couple of days about a particle passing through a magnetic field, with one exceptional difference. The wire experiences the force, and it experiences the force all along the length of the wire. So if you have a wire where you can switch on and off a current, then you can set a wire into motion using a magnetic field. The force doesn't change direction. It's based on the shape of the wire. So if the wire is of a fixed shape and you snap on a current in a magnetic field, all of the wire experiences that force. Therefore, all of the wire is pushed in the direction of that force. This means you can start a wire into motion, and you can stop a wire from moving using a magnetic field. Think cheetah hunt. How do you think they propel it? They don't use this exact kind of idea. They use a similar idea, but you just run a current through the wire and suddenly you can start pushing on stuff. So when you start considering the implications here, let's look at a couple of ways that this could be used. The first one I want to talk to you about is called a Gauss projectile launcher or a railgun. I'm sure some of you have played video games or have heard of the idea of a railgun. Raise your hand if you've heard of railguns before. Anybody? All right. You can build a railgun out of a stapler if you really want to. It's got two rails on it, and you can shoot staples. It's not nearly as exciting as it sounds, and don't get your hopes up here. When we start seeing the reality of this, it's not nearly as useful as you might think. Isn't that tough? It starts with a couple of rails. So let's just say these are metal conducting rails. Then let's fill the region of space with a magnetic field. We've still not talked about where magnetic fields come from, but one thing at a time. Now, this alone won't do anything, so you need to find a way to generate a current. So one of the first things we do is we take and connect an EMF to the two rails. Then all we need is our projectile. So if we drop a conducting slug across the rails, something that will allow a current to pass from one rail to the other, then once we do that, there will be an instantaneous force on the slug due to the magnetic field and the current generated. A common example of this is to assume that the slug has a resistance of R and that the rails are very low resistance. First, using your rules of circuits, find an expression for the current in the slug. I'll give you a moment. There's not a whole lot to do here. I just want the current in the slug. first semester, late November, early December. My symbol for EMF, but yes, that's all it is. So the current in the slug, that's it. Now, direction, it's not up. If we look at the direction of the current, it's going to go from the positive plate to the negative plate. So there will be a current generated in this way. So I expect the current in the slug to be downwards. Now, what is the direction of the force on the slug? Right? So it's going to be to your right, my left. So now, a couple of things about what this could mean. If you can find a way to make the rails have a low amount of friction, not easy to do, by the way, but if you can find a way to make the rails have a low amount of friction, no matter how many of these slugs are placed on the rails, since all the slugs would be in parallel, they should all have the same current passing through them. Also, if they all have the same current passing through them, they'll all experience the same force. So as long as you can maintain the potential difference and the magnetic field, you should be able to just drop rails on it and it'll just keep shooting stuff off as fast as you want. So you can probably continue to shoot, and the limiting factor would be how fastly you can load the ammo onto this thing. But there's lots of realistic things that are wrong with it. For example, you're not going to have friction-free rails. So eventually, you're just going to melt the rails with all the heat you're going to generate. So there are real limiting factors. Also, let's consider size for just a minute, since you guys need to have a little bit of this. Imagine that this is 0.5 meter wide. And let's say that this whole length is 4 meters long, something big, tank size. Currently, a tank can fire a slug at 5 times the speed of sound. That's about 1,500 meters per second. If you actually wanted to build this and have anything appreciable to what a tank can already do, what kind of EMF and magnetic field are we talking about here? Let's assume that the resistance of the slug is very small, say 1 ohm. And let's say you can do, not the impossible, but the improbable, a 20 Tesla magnetic field. I've given you lots of information here. And do you think you could use your physics knowledge to figure out what EMF would be necessary to fire the slug? You have a variety of methods at your disposal. And I don't know if you're capable of doing this or not. It's first period, and you guys tend to not be really ingenious yet. So let me tell you, this is a net force equals MA problem or a work energy problem. If you remember anything from first semester physics, you should be able to work this through. You'll need one more piece of information, the mass of the slug. And if we compare it to like a jacketed round from a tank, which is made out of depleted uranium, we're talking 50 kilos. So again, what kind of EMF would be necessary? What kind of potential difference would be necessary to launch it at 1,500 meters per second? And let's see if you guys can put all your physics stuff together, your physics mojo, and make this work out. David has an answer. What's David's answer?
I said it was 750 volts. What?
David says 750 volts. Yimo, what do you say?
I said 1,406,250 volts.
1,406,000. Who cares what the rest is? All right. That seems very different. Did anybody else offer a different approach or a different value? Did anybody else get 750? Did anybody else get 1.5 million? Well, I have one supporter of 1.5 million. I don't think there's any reason to use a motion equation, but you could. It's just that it's just one extra step. If I were combining all these things together, trying to find the right direction, I would start with net work. Because net work equals change in kinetic energy. The object goes from 0 kinetic energy to a kinetic energy equivalent to 1,500 meters per second. So it looks like 1/2 mv final squared minus 0 is going to equal force times delta x. The force is going to be IL cross B times delta x. Any question yet? I is going to be the EMF over R times L times B times the sine of 90 degrees times delta x equals 1/2 mv squared. And I think we can solve this for the EMF. Any question about where any of that came from? It is all right here. Now, the sine of 90 is just 1. Resistance is just 1. The length is 0.5. Right? The length is the length of the wire exposed to the magnetic field. Delta x is 4. That's how far the object moves under the action of the force. Magnetic field, 20 Tesla. I think we can solve this for the EMF. So the EMF will equal, well, mv squared times r all over lb delta x. Oh, 2. Let's put the 2 there. Well, let's see. I think we're looking at something that's going to be bigger than 750. Mass 50, V 1500 squared, R1, length 0.5, B 20, delta X 4 times 2. It's going to be hard to get around that 1500 squared. Now I'm thinking 1,400,000 volts seems plausible here. Now you could try and make your projectile smaller. You could try and make your magnetic field bigger. You can make the whole thing wider. I mean, look at where all the numbers end up being though. The length ends up being in the denominator. If I make it bigger, wider, I need less EMF to launch my weapon. But ultimately, if I want to make it go, it's going to be tough, isn't it? And this is why. And the truth is, this is still based on reality. The current is going to be the EMF divided by the resistance. If it really has a resistance of 1 ohm, that's 1.4 million amps. You're going to melt the slug. It's just not particularly realistic. So there are other ways to make this work. Making the barrel longer, that clearly would help. But that gives you a linear response. You make it twice as long, you're going to have twice as much kinetic energy added. That doesn't make it go twice as fast because the velocity is squared. So as a weapon goes, although they're experimenting with them, you can see that there are some gross limitations as to what you can do. The truth is you ramp up the magnetic field because that actually has a tendency to do better for you than trying to ramp up the EMF and the current. But you still have massive limitations on what you can do. The truth is earlier this year, at the very beginning of the year, you made a simple motor. Do you guys remember? Later this year, you're going to make a more complicated motor. But the simple motors that we made were just a battery, a single wire, and a magnet. You guys remember? And it kind of just spun around the outside of the battery. Let's consider a magnetic field in a region of space that goes this direction. And I want to put a square of wire in the middle of this magnetic field. And put a current in the wire that goes in this direction. Now, this might be difficult to see, so I want to draw this two different ways. I want to draw it the way we see it here, and then I also want to turn it on its edge. So we're taking the whole thing and turning it this way, okay? So the magnetic field will still be to the right. But the current loop we're going to see on edge. So the current loop is just going to look like a line to us, with a wire here with a current going into the board and a wire here with the current coming towards us. Do you follow what I'm taking? I'm taking like this current square and I'm turning it. So we have a wire going this way and a wire coming this way. Does that make sense? There's also a current going this way and this way, but it's hard to draw that. You'll see why I've left that out here in just a minute. If I use my right-hand rule, the way it is now, and look at either one of these. So I look at this one, I'm noticing that my thumb goes into the board here. My thumb goes up here, right? Or well, my thumb goes into the board here. My thumb comes out of the board here, and also this wire and this wire, no magnetic field. But this wire force into the board, and this wire force out of the board. You guys see that? This wire force downwards, this wire force upwards. So there's going to be a force downwards here, a force upwards here, a force into the board all along this portion of the wire, and a force out of the board all along this portion of the wire. Do you see how that's clearly going to cause a torque on this wire loop to get it to turn? Can you guys see that okay? Now, that seems great, except first, how do you get the current into this thing, right? If this is a closed loop, would you put a little tiny battery in there somewhere? And you could. You could put like a little tiny EMF right here, and the whole thing turns. That's generally not how we do it, and you'll see why in a minute. Because as this turns, we'll eventually reach a point where my current loop makes it to say here. And again, right there at the top, I have this current coming out of the board and this current going into the board. True? You guys see what's happening here? The problem is that as it flips, the force stays pointed in the same direction on both of these. If you do your right-hand rule, you'll notice that's still true. So this will get my loop to turn, but it's going to orient itself with the magnetic field and then probably not stop. It'll probably pass and do this until it eventually comes to rest. If only when we got to the center, we could reverse the current. Like, imagine what would happen if just past that point, oops, I don't want to do that. say right there, what if we could suddenly force the current to reverse right when we pass center? The moment we do that, the moment it reverses, suddenly there's an upward force on this wire and a downward force on this wire. You guys see that? So, something like that. And that's going to cause this current loop to flip again. Of course, it's going to try and align itself with the magnetic field, and the moment it gets to the top, I would like to find a way to make it flip again. Do you guys see what I'm trying to do here? A reciprocating electric motor. Go ahead, David.
Out of the board and
So the two wires will experience equal and opposite forces. You see what I'm saying? And you're right, because there's a current that's going, on the outside wire. The one that is, remember this whole thing is supposed to be this. So there's a current going this way on one of these wires and this way on the other, right? So the one that's going this way plus that's got a force into the board. And the one that's going up has a force out of the board. So the net force is 0 laterally, and doesn't cause a torque because of the direction. In fact, the net force on this loop is 0, right? Up force and a down force, that balances out to 0. An in force and an out force, that balances to 0. So if we put this in the magnetic field and there's no gravity, it will be suspended and it will flip. But there'll be no net force to push it up, down, left, or right. But we do have forces on just 2 of the wires that will cause it to turn. Of course, we do have to get the current to flip at the top. Now, the way you get a current to flip is by having what's called a brush. How many of you have heard of brushless motors and brushed motors? 2 of you. Well, 3 of you. A brush motor is simple, and it's really easy to make. In fact, the kind of motor we're going to make is a brushed motor. And the brush just refers to how you deliver current to your loop. Instead of actually making a loop like this, this picture here. Because if this is the torque arm, this would be the angle between the force and the torque arm. It's approaching 180, and sine of 180 is 0. Okay, so far? Because here, the angle is 90. I'm looking at some faces, like Gabby's face, and making sure we're seeing this. Okay. Do you see that this is the force, and this is the length of the torque arm? Okay. And that's 90 degrees when the loop is oriented like that. So for R cross F, that'd be R times F times the sine of 90. So it would be maximum torque right now. But as it turns and gets like here, this angle is getting bigger and bigger and bigger and approaching 180 degrees. So like right there, it's pretty close to R times F times the sine of 180. So the torque isn't constant the whole time. The torque is changing as the motor's moving. Is that okay? I had a feeling if I turned it and showed this, it would be better. Is you take, and we would never actually make our loop square, but Mr. Shelton. So you take and you have your wire, but you don't close it completely. And these 2 pieces are your brushes. And you have a battery and 2 parts that come and make just very subtle contact with either side of the wire, so that when it flips, the contacts switch sides. You guys see that? That's how you make a reciprocating motor. So you're constantly flipping the direction of the current through your loop. So the moment it turns around and hits the other side, the current switches direction. And that forces the motor to flip around again. One of the problems with this is, as you can probably imagine, if you're not careful, your motor could get kinked up one direction or the other. It is possible if you don't get the current to flip soon enough, or the motor doesn't have enough inertia to pass the top center, then it won't flip the current in time. So a lot of times motors will have multiple axes, meaning multiple loops that are constantly experiencing that force all the time. So if you have one that's lined up with the field, you may have another one that's not lined up with the field at the same time. Well, we're going to build these next week. We're going to build simple, single pole motors. They don't flip the current because we're not going to make multiple brush directions. What we're going to do is we're going to have a motor that when it flips over, it just turns the current off. And then the inertia allows it to flip back and then turns the current back on. So we're going to make a single pole motor that doesn't have two power strokes. It has one power stroke and then no power stroke for the other half turn, and then a new power stroke again. They're fairly straightforward. You guys probably saw the ones we made last year. That's what we're going to make. We're going to do that probably Friday of this week, maybe Monday of next week. We don't have school Monday, Tuesday of next week. Does that make sense? Really depends on how far we go. Now, I'm going to stop here. Oh, I was looking at the wrong time. That's only 6 minutes. That's probably not enough time for you guys to do anything, is it? You guys have to do more lab? All right, so first 15 minutes of class tomorrow if you guys have to do more lab. For those of you who don't have to do, I make too many assumptions, and I need to check something really quickly. If there were a magnetic field here, and I tell you that this is length S, and it's a square, and right now the current is going this way through the loop. If I said all of those things to you, and I don't know, made it so that we knew that this was an EMF, maybe this has a resistance, the loop has a resistance of R. I'm just trying to put some variables out here, and then ask you like a question like, can you calculate the torque on the loop? Would that be something that you could do with your knowledge base, or do you not remember torque? So before I suspect that you remember torque, should I remind you what torque is real quick? Okay. Do you remember that torque is when a force is used to twist or turn an object?
Yes.
Okay. So, and based on what we've already talked about so far, this magnetic field is in the wrong direction to cause this. So let me use a magnetic field that's in the right direction. Let's just use the same magnetic field as before. If I use this magnetic field, will you recall that based on what we just did, the force here is, looks like it's out of the page on this side and into the board on this side. Can you guys right-hand rule that and make sure I'm right? Is it opposite? Yeah, it's opposite. Sorry. Sometimes I think that you guys will have no difficulty remembering last year, but so if you don't remember, torque is a cross product of the torque arm length times the size of the force. What's the torque arm length here? S over 2, right? Do we all see that it's S over 2? Because it's going to flip along its center. So this represents the torque arm length. Okay? The cross product is the direction between the force and the torque arm. So when it's like this, it's 90 degrees. But the moment it starts to turn, you understand that it's going to be reduced. So the torque isn't constant on this electric motor. It's turning towards 0 as the loop turns. You guys see what I'm saying? Because the forces are staying in this direction. So as this whole thing turns outwards, and the force still stays this way on this part, the angle is going to get closer and closer and closer to 0. So this goes from a maximum torque now to 0 torque when it is turned. The force doesn't disappear, just the torque disappears. Sound good so far? I know some of you are saying yes, but don't really believe that. You should work out